Good afternoon, everyone. My name is Professor Roger Woods, and I'm the Pro-Vice Chancellor for the Faculty of Engineering and Physical Sciences here at Queen's University. So let me give you the warmest welcome to the John Bell Day Lecture 2024. John Stuart Bell has had a lasting influence both for Northern Ireland science, but in particular for Queen's University, where he obtained a bachelor's degree in experimental physics in 1948, and a year later, a bachelor's degree in mathematical physics. His research has made a major impact in quantum mechanics, and his theories and research advances continues to make a major contribution, as evidenced by the title and content of this lecture. The university are immensely proud to be associated with John's work and have highlighted his legacy both in terms of creating this special lecture series, but also naming both a lecture theatre and a student house in the university in his honour. The blue plaque commemorating him in the university's main campus represents another permanent acknowledgement. However, I think the biggest acknowledgement comes from the statement of a well-known physicist who said that there's often forgotten but nevertheless crucial discovery in physics that, in my opinion, surpasses all others. By that I mean the pioneering work done by the physicist John Bell on local hidden variables of quantum mechanics, which ultimately led to his ideas on non-locality or Bell's inequalities. The well-known physicist who made that comment is actually today's speaker, Nicolas Gisin from the University of Geneva. Our speaker made that comment on his book review for John Stuart Bell quite a number of years ago. Therefore, it gives me great pleasure to, on behalf of the university, to ask Nicolas to give his presentation. Thank you.
Thank you. Thank you very much for this introduction and reminding me that I had written that when you were mentioning it was sounding familiar, and I was thinking, yes, that's something I could have said. I didn't know that that you were actually referring to me. So let me now try to share my screen. Share, okay, and now I come to this one, that one. But it should be at the beginning here. Okay, do you see my screen? Is all fine? Oops, no. Here. Do you see my screen? Should I start now?
Yes, it's perfect.
Okay, very good. Okay, so it's a great honor to be speaking here. 60 years of Bell inequality is quite a nice number. Moreover, I knew John Bell not only from his inequality, but we met in person in Geneva. He was working at CERN, I was working at the university. Of course, I was way younger than John. Nevertheless, we had some fantastic evenings also together with his wife, Mary. So the title, as you can see, is From Bell Non-Locality to Quantum Communication. And at the end, we also go back, pointer, here. This is not a nice one. Here's a one, yeah. So at the end, we go also back to network non-locality, and I hope to show you how beautiful results we get out of that. But let's start, since physics is an experimental science, with this experiment by Alain Aspect in '82 that led him to win the Nobel Prize 2 years ago. So here, I'm going to explain you everything, but essentially, so the source of two photons was this atomic cascade there, and you see this pipe, which was not guiding anything like light or photons, it was just to protect the path of one photon. You have the same going in the opposite direction, so altogether it's about 10 or 12 meters long. And so with that, Alain was able to demonstrate a violation of these famous Bell inequalities, more specifically the CHSH, closer-Horn-Shimony-Holt inequality. So the detector would be one which you don't see, which is in front of us, and the other one behind the wall that we also don't see. So at that time, in the early 80s, I have to say that this kind of experiment fascinated me absolutely. but not many more people. I mean, there were a few, of course, I was not the only one, but most people really didn't find that too exciting. And I would call that the curiosity lab, because not so many people really paid any attention. So maybe I don't want here to derive Bell inequality, but maybe just to remind ourselves how it goes. So you start from some state of two particles. Let's think of two photons. And you may think of one being blue and the other one being red. So they can be distinguished so that you can send the blue one to the left and the red photon to the right-hand side. And then on both sides, let's look at the right-hand side here, you have a mixture of these phi1 and phi2 states. So you get this mixture. And then you can have a polarizer or any analyzer here. And this analyzer can be oriented, so adjusted. Maybe it will also be interferometers later, so it could be a phase of an interferometer or the orientation of some polarizer. But all what you see on these single photon detectors, so these single counts, is something which is flat, which does not depend on this parameter B, this experimental parameter B, on the orientation or the setting of the analyzer. And it's the same on the other side. So if you just look locally, it's very boring. You don't see anything. There's no structure. However, since you have two photons, you can now look for coincidences. You bring this signal, these classical signals together, and you can measure coincidences. And when you look at the coincidences, then here on the contrary, you have a huge structure in the signal. You see these sinusoidal interference fringes. Of course, it's two photon interference fringes, and very remarkably, they really depend on the difference between the settings. It's really A minus B, depending. Sometimes it could be A plus B, but that amounts to the same. So you have that, and you get this structure. Then you can analyze all that, and that's what John Bell did 60 years ago. And if the statistics of this correlation cannot be described by local variables, then we speak of quantum non-locality. So when I will say quantum non-locality, I just mean that the structure that we observe in these coincidences cannot be described by local variables. Okay, so I'm not going to show any Bell inequality. I think you had that already in the previous years, and today this is pretty well known. But let me see what comes after that. So one of the things that we did, okay, here I'm speaking of Geneva, you know, in 15 years after Alain Aspect, we could now go out of the lab into the Swiss telecom operator optical fiber network. And so we had a source somewhere in the middle of Geneva here, and then we had one analyzer in this village, Bellevue, the other one in Bernay, about 10 kilometers, a bit more than 10 kilometers apart, so 1,000 times larger than an aspect distance. And we get again these sinusoidal oscillations in the correlations. Visibility is not 100%, but by far sufficient to violate Bell's inequalities. Very nice. And then clearly one is fascinated. So there's this intellectual fascination. Questions like, how does nature do it? How can you non-locally correlate or coordinate? This is really fascinating, and I think it is still a topic of fascination today. But physicists should ask not only that question, they should certainly ask this question, how does nature do it? But there's a second question, which physicists sometimes tend to forget. The second question is the following. What can we do with these entirely new kinds of correlations? Now, if you have something which is completely new, and these two photon interferences at a distance, Bell inequality violation, is something completely new. So if you have something completely new, it must have some kind of applications. And this took a long time before someone came up with a good idea. And that idea is due to Arthur Eckertz in 91. At that time, Arthur was a student, PhD student in Oxford, yes. And so he noticed that actually these non-local quantum correlations are cryptographic keys. And that's an enormous change, because before you had just Bell inequality, intellectual fascination, and all that, which is, of course, super important for physicists. But now we have cryptographic keys, something really useful. And that changed the entire situation. I personally believe that this paper is really the beginning of quantum information science. So how does it go? Let me stay on the intuitive level. So we have our friends nowadays, we call them Alice and Bob, and they have some boxes, but these boxes don't need to be characterized or trusted. Or let's say Alice and Bob are bankers and they don't understand quantum physics. I can guarantee that, by the way. And so what do we do? First, we need to exchange some quantum schmantum. So we exchange some photons in practice. So you have to open so that you get these photons going within these boxes. Then we close the boxes, and only at that moment, box closed, we choose, or Alice and Bob choose which measurements to perform. So we choose one orientation for their polarizer or one phase for their interferometer. So they know that, okay, X on Alice side, Y on Bob's side, needs, of course, to be at least a binary choice. And they get also at least binary possible outcomes, A and B. Next, they repeat that many, many, many times, and then with a public announcement of a fair sample of their data, they can do some statistics, and from these statistics, they get a good estimation of this conditional probability distribution of obtaining outcomes A, B, respectively for Alice and Bob, given measurement settings X and Y. And this is the probability distribution that could possibly violate a Bell inequality. And if this does indeed violate some Bell inequality, then at least intuitively, it's very simple. Violation of Bell inequality excludes possible local variables. But if there are no local variables, there is nothing to be intercepted here. So if you have an eavesdropper in between Alice and Bob who would like to intercept the key here, in this case, the cryptographic key, well, violation of Bell inequality means there is nothing to intercept. There are no local variables to be intercepted. And the quantum state, as probably everybody knows, cannot be cloned or cannot be copied. So here you get then secrecy, because impossible of copying, irrespective of any implementation detail. So something very important. Nevertheless, this intuition, Arthur's intuition in 91, it took, well, 15, a bit more years until you really had a proof of that. So here you have papers with proofs, mathematics, and so on. And I'm not going to present proofs today, but you see that this is not it's not trivial to go from the intuition to a mathematical proof. Let's also see how we go from the experiments of a Bell inequality to this quantum key distribution, so the cryptographic key. So we start with a source in between Alice and Bob, these two photon sources. And you see on both sides, you have a Mach-Zehnder interferometer with a short path and a long path. Okay. And then we have these detectors on Alice and Bob, and we are going to look for coincidences, as I have already said. And clearly, there are two possible ways to get a coincidence. It could be that Alice's photon takes the short path, and Bob's also take the short path. Then we will arrive at the same time. You get a coincidence. But of course, there's also the possibility that Alice's photon take the long path, and similarly, Bob's photon takes the long path. Then also we arrive at the same time. And as soon as we arrive at the same time and they are indistinguishable, so you need some coherence of these two photon source, you get, you know that in quantum mechanics, one has to add the probability amplitudes and not just the probabilities. And so you get these two photon interferences. Okay, very nice. So that's one way of, and that's actually the way we used when we did this violation of Bell inequality outside the lab between Bellevue and Bernay, the two villages I mentioned before. But now if you want to do that really practical, it's not very practical here. Of course, you have Alice and Bob, that's unavoidable, but you also have this third party in the middle. So obviously the first thing to do is to remove the third party and put it, let's say, on the left, on Alice's side. Okay, that is already an interesting progress, because now what comes out of Alice is just a single photon. So at the end, you have already the idea that everything can be done by just sending single photons from Alice to Bob. But let's look at that a bit more. So we are in this situation. Now what we could do is to put this 2-photon source here on the other side of the interferometer. Doing that, we do in practice what theorists know well. If you have a maximally entangled state, here written for qubits, and you act on one side with this interferometer, this imbalanced Mach-Zehnder interferometer with this U now, you can as well act on the other side. Now, instead of acting on the photon going left, we act on the photon going to the right side with this transpose unitary. And so here what we can see is now you have interference between the photon going short path on Alice, long path on Bob, to a detector here. This will interfere with going first long, next short. Again, you get good timing when you need some electronics for the time. Okay, that's already a big progress. That's actually the kind of configuration that Toshiba uses for their commercial QKD systems. But you can still make it a bit simpler. You see, one of the difficulty here is that you have 2 interferometers, and clearly the difference between long and short paths on Alice and on Bob's side, both differences have to be the same up to the coherence length of these photons. Let's simplify that. And this sounds like a huge simplification. Now I have a mirror here. And I put actually my detector here. It's not shown, but it is here. And now what do we have? We have interference between going straight to the mirror and on the way back, taking the long path. That's one possibility. This is going to interfere with first going the long path to the mirror and back via the short path. And you get, of course, with the same timing to this detector, hence again interferences. This is not very good because now the distance Alice Bob has to be traveled twice. And if you send a single photon over twice the distance, of course, the losses will be twice as large. So let's put an attenuator here, and we send a bright pulse here, many photons, and we attenuate it on the way back from Bob to Alice. So kind of, although Alice sends plenty of photons to Bob, Bob sends only a pseudo single photon back to Alice. Next simplification would be to replace the mirror by something which is called a Faraday mirror. And a Faraday mirror is something that does some analog to phase conjugation, but on polarization. So every polarization state that arrives here will get back in the orthogonal polarization state, and all the polarization fluctuation that happens in these long fiber. Here you have to imagine 100 kilometers of optical fibers. So all the polarization fluctuation undergone by the photon going from Alice to Bob will be undone when going from Bob to Alice, so that you get maximal interferences. And finally, you add a polarization beam splitter here, so that everything that went to the short path here, since it comes back orthogonal polarized, it will take the long path on the way back, and vice versa. Everything that takes the long path on the way to Bob, on the way back, will get straight the short path. So once you are here, you put the Lake of Geneva in the middle, and you get Nature papers and so on. So that was actually my first Nature paper. And moreover, if you have a good student which has some energy, a lot of energy, I have to say, and has some entrepreneurship, then you can make a spin-off or a startup. And see, this is now 23 years ago. That was at a time when startups were not as fashionable as today. And so we established this spin-off. So here you see one of our first QKD engine, this one here. So this one produces the QKD, so the cryptographic keys. These cryptographic keys are then used by these boxes that do the encryption and decryption. And so this is now used, for instance, not as a demonstration, but really as a commercial application. Okay, but that was years ago. Today, QKD boxes, they look like that. So that is standard 1 unit thickness and so on. And essentially, these boxes, you just have a photon coming out on one side, going to the other side. So this is also no longer exactly the same protocol I showed you, but similar. Okay, very nice. And once you have that, you have networks going on. Here's an example of a network for the South Korean government. It's a very complex network with many nodes and so on, a lot of activities going on. You have also such networks in Poland, for instance, to take a European example. Okay, good. Now let's step a bit back. So here we went quite fast to quantum technology, quantum communication technology. Let me come a bit back to the basic. So this principle of continuity. So correlations, according to classical physics, have only two types of explanations. It could be just a local common cause, so these local variables, as we mention, as we talk, following John Bell's influential terminology, or it could be just influences. I'm influencing you presently, or was also indicated here. So you have just communication, direct communication, or direct influence. And indeed, a lot of efforts have been produced to exclude common causes, so the so-called local hidden variables. But what about hidden influences? So could there be a privileged reference frame, like for instance, the frame in which the cosmic microwave background radiation is isotropic? And if there would be such a privileged reference frame, we could even consider faster fine light communication without grandfather paradoxes. And this is actually something that Bell himself was really very keen in promoting. David Bohm, also emphasized that one should exclude also this direct causation. And also in textbooks, very often you read that a first event collapses the entire wave function, so also has a spooky or not spooky action at a distance. So let's try to do that. We go back to two villages near Geneva, and they are east-west oriented, as you see, more or less. And we try to do these experiments with very good timing. So we have a source here in Geneva, these optical fibers, still from Swisscom, and we want these detectors to have very good time resolution, and the two photons arrive really at the same time, as precisely as possible. If we do that, comes, of course, the question, in which reference frame should these two events here, the two detections, be simultaneous? And here you can, of course, you know that according to relativity, it depends on the reference frame. So let's do it indeed this east-west orientation between Alice and Bob, and do in the Earth reference frame a very good synchronization, because it is very well synchronized according to this reference frame. Now it will also be perfectly well synchronized according to any reference frame that moves perpendicular to this AB direction. So perpendicular means a plane passing through the north and south pole of the Earth. And now you will do that continuously during 12 hours. And this plane is going to rotate. And in 12 hours, is going to scan all possible hypothetical privileged reference frames. So if you do that continuously during 12 hours, you are fine. And so this is what we did. And these are the results. So here is the bound on these velocities. You see something like 100,000 times the speed of light. Why is that not exactly flat? Well, it depends on the orientation of this privileged reference frame. We were not exactly east-west oriented. There was something like 5 degrees off. So this is this strange curve here because of this 5-degree off. Anyway, we get some results like that. Nice results that have been also reproduced by several other groups worldwide. And we see that indeed at the end, so we exclude, let's say, something like 100,000 times the speed of light direct communication. That's already very fast. And understand also that this is important if you want really that cryptographic keys are secure, because so there are no local variables, that's Bell inequality, but if there would be something directly flying from Alice to Bob, of course, one could intercept it. So you need also to exclude this direct communication. And with two parties, there is no way to do better than, okay, you can improve these experiments, but you will never be able to get to unlimited velocities, because every experiment will have only finite accuracy. However, there is a remarkable theorem that goes a bit beyond standard Bell inequalities, which states that if you have 3 and 4 parties, so more than 2, you need more than 2, then in these kind of scenarios, you can really have a scenario in which no explanation of the quantum correlation or the quantum prediction with finite speed influences can remain hidden. So you would notice it, you would necessarily notice it. And so if you believe that these hidden influences should not allow one to communicate faster than the speed of light at a macroscopic level, then you can exclude them. So all direct causes lead either to infinite speed or to the possibility of faster than light communication at the level of classical measurement settings and results. So admittedly here, I did not tell you how this theorem is proven. It's complicated. It's again in this Nature Physics paper. I just wanted to mention that because I think it complements Bell's work very nicely. You really can exclude both the common causes and the direct causes. So because of this result, now we could say that there is no spooky action at a distance. There is not really a first event that influences a second event. It's really one non-local event that happens. Let's continue with that and continue in the following way. So we still have our source of entangled photons, so 2 photons going to Alice and Bob. And we know that if we now if Alice, for instance, does a measurement in the vertical basis, so a Z basis, as we say today in quantum information, she's going to prepare for Bob either spin up or spin down. On the other side, if Alice measures in the horizontal basis, the X basis, she's going to prepare for Bob either right or left state. However, the two mixtures correspond to the same density matrix, so they cannot be distinguished. And for that reason, you cannot use entanglement for communication. So entanglement does not allow for signaling. Good. But now let's suppose that we have some clones here. So we could do some cloning. Then Alice measuring in the vertical basis, so the Z basis, she would produce after the cloning machine here, 2 vertical photons or 2 vertical spins for Bob or 2 down. And Alice measures in the horizontal basis, the X basis, she would produce either these 2 or these 2 here. And now the 2 density matrices, the 2 mixtures correspond to different density matrices. And because they are different density matrices, if you could clone here, then you could signal. Perfect cloning would allow one to exploit entanglement for signaling. Okay, there is no signaling according to relativity, and we understand that here. However, what if here I do the best I can do, no? Laser amplification. We know that stimulated emission is really doing cloning. Stimulated emission is precisely cloning. However, stimulated emission always comes also with spontaneous emission, and spontaneous is in all possible directions. So there is no cloning here. There's some noise here. So let's look what we could do here. And here I introduce the famous A and B coefficient that Einstein actually introduced, I don't know, almost 100 years ago now, not quite, but a long time ago. And so you really have, if you start from 1 photon in 1 mode, let's say vertical mode, for instance, and you create a second one, you get 2, of course, you get 2 photons with these coefficients, or coefficient here, random variety amplitudes. And if you start from 0, you have only the A coefficient that applies here. And from that, you can now compute what could be the fidelity on Bob's side. So if it's stimulated emission, so with probability B plus A, then the fidelity is perfect because stimulated emission is a perfect cloner. However, if it is spontaneous, then actually it is like noise, and noise in terms of these fidelity units is 1/2. Then you normalize, and you use the fact that already Einstein knew that actually A is equal to B. That's actually his famous result, Einstein's famous result with his A and B coefficient. And now you can do the computation and you get this fidelity 5/6. And this is really remarkable because this is precisely the optimal quantum cloning. So these stimulated and spontaneous emissions here are exactly at the limit of allowing signaling, allowing one to use entanglement for signaling. Okay, it is just 5/6. It's not 5/6 plus any epsilon. So you cannot signal, but you're really at the limit. And you can even prove that more generally, not even using stimulated and spontaneous emission, you can prove that this is indeed the limit, the possible limit. So we see, and here now, connecting Einstein and John Bell's work. So the AB coefficient actually implies, okay, no action at a distance or no signal. Of course, it would be now very fascinating to ask Einstein, who of course understood the AB coefficient extremely well, why he could not apply that to entanglement. Probably too much demanding. Let me just really emphasize that any epsilon increase in stimulated emission without a proportional increase in spontaneous emission would immediately allow one to use entanglement to signal at an arbitrary fast speed, and vice versa. You can even now do some experiments here. Just use an optical fiber doped with erbium ions, and then you can have this stimulated and spontaneous emission. When you send in something which is polarized horizontally, you split horizontal for vertical. With that, you can measure the fidelity, and you can do that, and you see that the theory and the experiment match extremely well, and that is a nice outcome also of this connection between the AB coefficient and no cloning. And this is really something which is actually even considered by some laboratory to define the radiance, so to do radiometry. Another consequence of this no action at a distance that we just derived comes from this situation, again, a standard Bell inequality test scenario. And here we have the following theorem that says that what comes out here on Alice, and the same, by the way, on Bob, so the A and B, just assuming no action at a distance, and also assuming that they exist independent systems. So I can choose this X, the inputs, the orientation of my polarizer or whatever, and Y here, independently. Then this is really random. So we get randomness out and certified by a violation of Bell inequality. So you see now we have from AB coefficient, we get no action at distance, and from no action distance, we get that God does actually play dice. Again, it would be fascinating to ask Einstein what he thinks of that. I don't think that John Bell understood that his violation of his inequality would necessarily imply that God plays dice, because the theorem didn't exist. But I'm certain, because also of my discussion with him, that he really understood it, at least on the intuitive level, probably without the theorem that I just mentioned. Now, once you have this randomness, you can also use it to just make a random number generator, a quantum random number generator, as you see it here. And so this was produced by the same company that I already mentioned years ago, and has been certified by all these certification agencies. For instance, here, that's the French military system. This is the Swiss metrology, and so on. But let's go further. So here, 4 centimeters, that looks very nice and small and compact. But now you go to engineers, and engineers are remarkable persons. You give them that, and they give you back a millimeter-size quantum random number generator, which moreover consumes very low power. And once you have it on that size and that power consumption, you can put it into a smartphone. You see, this is a Samsung smartphone. They call them the Quantum Galaxy phone. Unfortunately, this is commercialized only in Korea so far because all applications are in Korean. And nevertheless, you have millions that have been sold now. And so you have here a first mass application of quantum technologies, or you may say of Bell inequality violations. Here I want to say a bit more about single photon detectors because this is another remarkable application of following these quantum technologies. So here it is superconducting nanowire single photon detectors, so SNSPDs we call them. These are the best detectors you have today. You see more than 90% efficiency. When I started, we were very happy with a few percent efficiencies. And you have photon number resolving detectors. So this example, you can detect up to 8 photons. I think today we can even go up to 12, something like that. Okay, what is that good for? Of course, it's good in laboratories, university laboratories. But I want to show you another application, a very different sort of application, an application of single photon detectors to rockets. So this is Ariane 6. The first Ariane 6 flew for the first time last July, I think it was, a few months ago. And this is the first rocket that doesn't use electric cables inside, but only optical fibers. And also to trigger the engines, you see these engines, you have many engines in a rocket actually. To trigger the engines, the way it goes, you send a bright light pulse on something that will heat, so on some pyrotechnical element, written here, optopyrotechnics. So this heats, and then boom, the engine goes on. The problem is that before launching such a rocket, you need to test all these optical fibers. And how do you test your optical fibers in general? Well, you send an optical pulse, and then you look at what comes back. The problem is once you have sent your optical pulse, the engine goes on. And you want to test the system without the engine going on. So here, the solution was to use what we call photon counting optical OTD, what is T now? Transmission reflectometer. Optical time domain reflectometer. Sorry, optical time domain reflectometer. So you send a pulse, you look at the photons coming back, but you send a pulse which is so weak that very, very little comes back. So little comes back that is not going, so little enough goes to the engine that the engine doesn't go on. And so little comes back that you need single photon detectors to be able to detect them in this box here. So you have many of these SNSPD detector here. And so this is a very, very different kind of application of quantum technologies, nothing to do with communication, with computation, it's more with sensing here. And it is surprising and very nice. But now we went, I think, very far down to what's quantum technology. So let me go backwards now and see how what this implies now for quantum networks. The network I showed, for instance, in Korea was a kind of not completely quantum network because we had what we call trusted repeaters. So we go from quantum to classical and back from classical to quantum. Here, let's suppose that this is really a purely quantum network. So you see many sources. So one source between Alice and Bob, one source between Bob and Charlie, and so on. And here we would do teleportation, so Bell state measurement, so like entanglement swapping, different ways of saying the same. We would teleport the entanglement here. And we assume that all these sources are independent, just an example of a network. So now the question is, how are we going to certify the quantumness of such a complicated network? And here we're going to go back to the intuition of John Bell and replace these sources, these quantum sources, by shared randomness or local variables, if you like. So we have now a source of local variables between Alice and Bob, a different one between Bob and Charlie, but we're going to assume that they are independent. We go back here to the quantum case, this source could be powered by solar energy, and this source could be powered by a university professor on his bicycle, for instance. Then clearly they are independent. So here we do that, and we really imagine that every source is carrying its information, its structure, or its instruction with these local variables. So this is really the John Bell view here. And so here we have the simplest network, which is just entanglement swapping, but you understand that now the usual definition of locality, which here we call bilocality or two-locality, because we have two sources, you again have these local or hypothetical local variables that we want to exclude here, when the outcome probability for Alice depends on her measurement setting and on the variable she has access to. Bob has access to both variables, Charlie again to only one. And you see that the two variables are assumed to be independent, so their probability is factorized here. And because of that, the set of these bilocal correlations or probabilities is not convex. So you don't have the usual scenario with local polytopes and things like that, and Bell inequalities being a linear facet or a linear inequality. And here, I just give you some example. So here is, for instance, so the square here would be a local polytope, and each of these facets is a Bell inequality. And here in the center, we have the non-convex set of bilocal correlations. And so you see, we can exclude way more. So it's way more noise tolerant. And you also see that in this example, this inequality here, because of the square roots, you see it's clearly highly nonlinear. Okay, so again, something new, so it must be application. So here the application is on something conceptual. I'm coming close to the end. Close to the end. So let's suppose we have just one quantum system here in d dimensions, so the complex number to the power d, and you can perform measurements x and you get outcomes a. Very banal situation. Now, we all know that this Hilbert space, complex Hilbert space, is isomorphic to a real Hilbert space of twice the dimension. And in order to double the dimension, you could just say it is r to the power d, so real Hilbert space of the same dimension, tensor a two-dimensional Hilbert space. So some people call that a real qubit or a rebit, I think they call it. And here I just illustrated with this green disk here. So you can do that. And of course, so it means that you can obviously do everything in a real Hilbert space. You don't really need the complex numbers. They are convenient, like they are convenient in electromagnetism, like they are convenient in relativity, but they are not really necessary. Let's go to a more complicated situation, like a Bell inequality situation here, but with three parties, so it could be any number of parties, but one source. So it's really Bell inequality in the historical sense. And here again, you have these three parties for this example of dimension d1, d2, d3. Obviously, this is isomorphic to a real Hilbert space of the dimension, the sum of these dimensions, tensor real qubit, R2. Now the problem is, where should I put this qubit here? If I put it on Alice's side, then Bob and Charlie cannot act on it. And if we put it to Bob, then it's Alice and Charlie that cannot act on it. So here we're going to get inspiration from a quantum error correction and use logical qubits. So for instance, we put three physical qubits, one for Alice, one for Bob, one for Charlie, and we define the logical qubit 0 as all the superposition with an odd number of zeros, and the logical one superposition of odd numbers of ones. And now everyone can flip the logical qubit by flipping the physical qubit that flips also the logical qubit. And so this is a result which is now already pretty old, 15 years old, that says that if you have whatever number of parties connected to one source, all Bell scenarios can be described using only real numbers. So here again, we are in the same situation as relativity, electromagnetism. Complex numbers are nice, useful, but they are not essential. However, now we go to this new scenario, entanglement swapping with independent sources. This one is solar power, this one is this university professor on his bicycle. And now if they are independent, you see that putting a logical qubit here will not work because a logical qubit by construction, by definition, requires some dependencies, having the total number of zeros being even or odd or things like that. So the trick we used on the previous slide will not work. You may say, okay, maybe there's another trick. No, there's no other trick because of this theorem. The theorem that says that in this entanglement swapping scenario, okay, we've quite some inputs for Alice and Charlie here. There exists some Bell inequality, which is essentially what we call CHSH3. You apply CHSH in the XZ plane, in the XY plane, and in the third plane, the orthogonal plane. And in this way, you can achieve as maximal value using standard complex quantum theory, 3 times the CHSH value, so 6 times square root of 2, while with real Hilbert spaces of any dimension, or just emphasizing real Hilbert spaces, we could prove that the limit, the maximum value of the CHSH3 expression is strictly smaller. So it is impossible to achieve the 6 square root of 2 with real Hilbert spaces. So we come to this remarkable result that in networks with independent sources, this cannot be described using only real Hilbert spaces. So let me really emphasize how profound this result is, because I think it's the first time in science that complex numbers are not just convenient, but they are essential. And of course, this has then been done experimentally in these papers. And okay, you could also reduce the number of settings a bit. And this you find more in this paper. Again, a Nature paper here. Okay, so at this point, I think we all agree on that question. And with that, just on time, I think, I come to the conclusion, and I think really the main conclusion of all that, and I think it's really a message that we also learn from all this, it's going from Bell inequality to quantum information technologies, is that we really need both basic science, undoubtedly, and technologies. And they really come hand in hand and both help each other to progress. Okay, so thank you very much. I hope you enjoyed this talk. Giving a Zoom talk is always a bit bizarre because we get absolutely no feedback, but I hope we are all on the same page now. Thank you.
Thanks, Nicolas. I don't know, can everyone hear me?
Yeah, I can hear you okay, Marty.
Perfect. So look, we have a relatively short question and answer session. If you have any questions, please write them onto the Q&A if you can. I'll pick them up and then I'll say them out loud for Nicolas to answer. So no one's had time to write any questions in yet. So let me ask on chair's privilege a couple of questions. Nicolas, you know I'm not a quantum physicist, so forgive me for the naivety, the inevitable naivety of these questions. You mentioned South Korea a few times, and I wanted to ask, what is it about the South Korean government or the culture in South Korea that means that it seems so far ahead in terms of the use of quantum communication?
Yes, this has almost to do with politics a bit. It is a fact that people in Asia in general are way more eager for new technologies than people in Europe. And so it's way easier also to develop these new things in Asia. In China, China is quite ahead in these quantum technologies, in quantum communication at least. So South Korea is very active. There's also now something, a network, of course, on a smaller size in Singapore, smaller just because the country is so small, and so on. So it is a matter of the fact that actually a lot is happening in Asia, and I think we in Europe should worry that things are just happening faster and with more enthusiasm in Asia than in Europe. There's also now things moving a bit in the US, by the way, but it's really clearly the continent that is driving that is Asia.
Interesting. So could you say a little bit more about the quantum number generator, random number generator that's in every, or in a lot of the Korean mobile phones?
Mm-hmm.
So does this mean that the normal punters are communicating on mobile phones with perfect
Well, so we use this random number generator indeed, and we can trust that these are really perfect random number generator. However, then we go and use it for classical cryptography with their banks, for instance, or hospitals. So we also you and me, everybody, we use cryptography all the time, most of the time without noticing. And at some point, you need a random number generator. And clearly, the best random number generator are these quantum random number generator. It's the only one that are really guaranteed to be random and not just pseudo-random or anything like that. And again, so this is a selling argument in Korea. And people like in Swisscom, just to mention our national telecom operator, doesn't think that this is going to attract enough traction in Switzerland to include it also, or to ask for a Swiss version of this Galaxy Quantum, which I find very regrettable. And I'm also not really sure whether this is really correct. Of course, people to whom I talk, but this is a biased sample, they would be very happy with such phones. But it seems seemingly the general public is not interested by that.
Amazing. So my last question, and then I'll move on to some of the things that have been written. We sort of think of quantum cryptography as a very positive, secure method of communication. But are there also threats associated with it? And what do you think about the positives versus the negatives?
Yeah. So this is again a kind of a political. Of course, if you have a hammer, you can use it to nail. That's you have the positive side, but you can use your hammer to hit your neighbor's head. And the same is with cryptography, whether it is classical or quantum cryptography. Of course, every of these tools can be used by the good guys. Let's say I would be happy to use quantum cryptography in my communication with the hospital, for instance. But indeed, depending who is using it, I understand that there is also some danger. And indeed, what is kind of becoming more and more the trend is that we have this trusted node where we go from quantum to classical and back to quantum. So at some point, the government may have access to some of these keys. If it is in a public network, of course, sometimes you also have a private network, a bank that has just its own network, then it is different. But if it is a public one, you could imagine that the government is enforcing by law that they have access.
Yeah, you talked about these trusted, what were they called?
Trusted nodes, trusted nodes, or trusted repeaters.
Yeah. So I guess that's a mechanism for the government to keep some kind of tabs on the communication.
Yes.
So I've got a question here. Sorry for my ignorance in quantum physics, but could I ask how many qubits in the QRNG chip that you mentioned in the presentation?
So this is 200 per chip. It's 250,000 per second. But then you have, these are also, for instance, they are now also on the Galileo system, the European Galileo GPS, they will be using these. And then you have more than one chip. I have this chip here. You can see them. I don't know how good you can see them. So this chip is 250,000 bits per second. Of course, you can put many of them on one PCI board. And if you have 10 of them, of course, you will get 2.5 million per second, and so on.
Amazing. So another question. Could you say a little more about the sources of entangled photons, or the sources of the entangled states?
So here I should distinguish for the experiments that we did and many people do. Most people use parametric down conversion in some nonlinear crystals. So this is way more convenient than the source that Alain Aspect and John Clauser used at that time. It's just a small nonlinear crystal, and it produces photon pairs. And then by energy conservation, you see that they have to come in pair because it's one high energy photon that splits into two lower energy photons that share the energy. But for the commercial systems, since we put everything on Alice's side, so what is coming out of Alice is just a single photon, and actually it's even just a pseudo single photon. Pseudo single photon means it's a classical laser pulse, or it's a weak laser pulse. So it's a weak laser pulse that is so weak that it has on average less than one photon per pulse. So of course you waste some time because sometimes you are sending out vacuum. But the number of two photons, the number of cases that you send actually two or more photons can be bounded very precisely. And these cases of multi-photons can then be post-processed in a classical post-processing where we do what is called privacy amplification, where we take a long string of bits with some potentially some information to the adversary and make it shorter, and in the shorter bit string there is zero information left to the adversary, to Eve.
Okay, thank you.
So the commercial thing is just a weak laser pulse.
Okay. So another kind of question. So Thomas has noticed here that you can look up a marketing brochure with the quantum random number generator chips. They exist online.
Yeah.
And I think he's asking, what order of magnitude is the price?
Well, so this one we sell for it's about what is it, $150 or euros. But that's if you buy a million. Now, if you want to buy only one, you probably better ask for a sample because selling one for that price it costs more than 150 anyway. But then what you can do also, I think even on the IDQ webpage, you can buy this kind of random number generator, which are mounted in little, it looks like a memory stick or a little thing. Because anyway, you need still some electronics around that. Yeah? So you need some power and some readout system. And you have to be able to connect it to your computer or to whatever you want to connect it. And so you can buy indeed quantum random number generator standalone that you can just plug into your USB port. And then there are also more let's say demanding customers, like for instance for these Galileo satellites, and they have really a board designed for their specific application. And then what costs is the development of the board.
Very good. Thank you. Okay, so one last question is, what do you see as the next great challenges then for quantum communication?
Well, I guess really in the laboratory, it's this to go away from these trusted repeaters and have a real repeater that really does entanglement swapping. So do the Bell state measurement and all that. And there probably the greatest challenge is really the quantum memory. You need to synchronize all that. You have photons coming from both sides, and they have to arrive at the same time. But because of the losses, even if the sources are super well synchronized, one will arrive before the other. And then in order to be efficient, you have to be able to store that one in a memory, in a quantum memory, wait a while, and then do the entanglement swapping with the second photon. So this is, I think, experimentally maybe the most demanding one. Possibly also to have better two photon sources. So these parametric down conversion sources is nice. It works very nicely, and we did a lot. People did a lot with that all over the world. But I think today it would be nice to have deterministic two-photon sources. So parametric conversion is a probabilistic effect. So you get it sometimes, and if you have students that have enough time, it's okay. But if you want to do something which is more commercial, it should be more deterministic, so that we can also go over longer distances. So that is really probably the main challenges on the, let's say, academic side. On the commercial side or the industry side, I think it is certainly, I mean, there is certainly now a pressure on the price, so the price should go down. Maybe the boxes can become a bit smaller, but it's really a matter of the price. And this is really a chicken and egg thing, because the market will grow if it is cheaper, and if the market grows, it makes it cheaper because we will produce everything not in batches of a few tens, but in batches of a few thousands, and that makes everything cheaper.
Perfect. Nicola, the time is past 4 o'clock. So we should probably wrap things up. But I have to say it's been an honor and a pleasure for us to hear the talk today that you've given. And thank you so much for stepping in at relatively short notice and giving us such a great and pertinent talk for the John Bell Day. Thank you so.
Okay.
And
Thank you,
everyone.
Thank you. Okay. Thank you.